Welcome students. In this video, we are going to discuss about the classification of HVDC links, and we will discuss about the HVDC components and its basics as well. So basically, HVDC systems can be categorized into three types. The first one is monopolar link, second one is bipolar link, and third one is homopolar link. So based on the requirements, I will select which link to use in which application. So let us start with monopolar link. Mono refers to single, polar refers to pole. So single pole link. Monopolar link has only one conductor with ground as return conductor. The conductor is usually of negative polarity. It is suitable for submarine systems where seawater is used as a return conductor. So let us see how a monopolar link looks like. So a monopolar link will look like this only. So this is what we call it as single pole. That is what we call it as only one conductor is used, which is usually of negative polarity. Why we are using negative polarity? Why not positive polarity? Positive polarity can also be used, but the problem is in negative polarity conductors, the corona loss is comparatively lesser. So when we are going for higher voltages and large amount of bulk power transmission, obviously the corona losses will be there in high voltages. So to reduce the effect of corona loss, we are always preferring the negative polarity. And here we can see we have only one conductor which is carrying the current, and we have the ground which is carrying the return path. So here we are using the ground as return path, or when we are transmitting power from one place to other place, if there is seawater in between the two places, then obviously seawater will be used as the return path. So there is some advantage of using this return path, but the problem is when we are using ground as return path, there is a lot of issues will come. So more problems related to ground will come. So there will be some interferences and there will be some corrosion issues, and the ground conductors may be broken. So all those issues will be there. So one more problem with this monopolar link is that it has only one conductor. If there is any issues in this rectifier, or if there is any issues in this inverter side, the total system will collapse. So there is no possibility of power transfer. So basically, we know that we are using HVDC system for its advantages on transferring the power with a very high suitability, and it does not have any issues. It has very good control. But when we are using the monopolar link, you can see if there is any single fault in this rectifier, the complete system will collapse. So usually we will not prefer this monopolar link, but it is practically possible. In our country, also in India, also we are using much of bipolar links that we will be discussing in the next class. Okay, so this is how a typical monopolar link will look like. This is not the exact picture. So for the purpose of understanding, I have just given you this picture where we are using only one conductor as a conductor which transfers the current. The other one is the return conductor where ground is used as the return conductor. And next one is the bipolar link. Bipolar refers to two poles. So bipolar link has two conductors. One is of positive polarity and the other one is negative polarity. Where the ground is maintained at the mid potential. Each terminal of the bipolar system has two converters of equal voltage ratings connected in series. If both neutrals are grounded, then two poles operate at equal currents, then there is no ground current. In the event of fault in one conductor, the other conductor will, with the ground return, can be used up to the half of the rated load or power with the rated current of the particular pole. So this is how bipolar link will look like. So when we are speaking about bipolar, two poles should be there. So this is one conductor which is carrying current ID1, and this conductor is of positive polarity. And we have another conductor which is of negative polarity, which is carrying a current ID2. So as we have already discussed in the previous slide, it has a mid ground potential. The ground is in the mid potential, so which carries a current which is the difference of these two currents. So why here one is positive polarity, other one is of negative polarity. So here when we are speaking about bipolar link, obviously you might have seen in many cases, you might have seen in many places whenever we are referring to that of HVDC links, will always refer it as plus or minus 800 kV. So why we are speaking about this plus or minus 800 kV? So plus or minus 800 kV refers to, plus refers to the positive 800 kV and minus refers to minus 800 kV. So majority of the HVDC links that are presently in our country are bipolar links only. So that is one of the important advantage. Another one is that, and as we have discussed in the previous slide, if there is any issue in this particular conductor for a converter, for example, this converter station, if there is any issue, that means this line will not carry current. So usually the current will flow like this. It will start from here, it will flow continuously like this in this path. But in case of any issue, in case of any issue in this converter station, or if there is any fault in this transmission line, so what will happen? This part will not be accessible. So this part can be opened, and once it is opened, we can use this path as the path of the power transfer capacity. So when we are using only half of the path, so here I am not using two conductor, I am using only one conductor, the ground as the return path. So if there is any fault in one conductor, the bipolar link will act as a monopolar link with ground as the return path. This is one of the basic advantage of the bipolar link, as it is having a very good reliability. Even if there is any fault occurs in one transmission line, the other transmission line can transfer power up to half of its capacity. At least 50% of the power is transferred. So that is one of the important advantage in the bipolar link. And next comes the, so this is how a bipolar link looks like. So two conductors and one more ground potential. Okay. So next one is the homopolar link. It has homopolar link. Also, homo refers to same poles. That means same polarity of poles will be used. So it has two or more conductors of same polarity, usually negative, and they always operate with a ground return. So again, why negative? So already discussed when we are discussing about the monopolar link. So negative polarity have less prone to corona losses. So even if we are using high voltages, the corona losses will be less in negative polarity. That is why we are preferring the negative polarity. In the event of fault in one conductor, the whole converter system can be connected to a healthy pole and can carry more than half of the power of two pole by overloading. But line losses will increase when we are using only one pole for the power capacity. Homopolar systems are preferred when continuous ground currents are required. So this is how a homopolar link will look like. The only difference between the bipolar and a homopolar link is that both of the conductors will be of negative polarity. So this is one conductor with negative polarity, and this is other conductor with the negative polarity, and this is the ground return which carries the sum of the two currents that is flowing in these two conductors. So as discussed in the previous slide, if there is any fault or if there is any issue with this converter station or with this converter station, this complete setup will not work. So the this conductor will allow the current flow with ground as the return conductor. Again, the homopolar link will act as a monopolar link. So that is the advantage of homopolar link. In many cases, we will be using in usually how we will how we will show the homopolar link like what we have seen in the bipolar link. So it will be just mentioned as you might have seen like minus 500 kV. So if it is just mentioned as minus 500 kV, it refers to just a homopolar link. And bipolar link, we will always refer it as plus or minus 800 kV like that. Okay, so this is about the basic three types of categories, that is monopolar link, bipolar link, and homopolar link. In majority of the cases, we will prefer only bipolar link. That is because of its advantages and all the things. Bipolar and homopolar are unifiedly used, but monopolar are very rarely used, and it is practically possible, but we are not using because of its disadvantage. If one pole gets affected, the whole system will collapse. This is the main issues with the homopolar link. Okay, so next we are going to discuss the basics about the components of HVDC system. So there will be many components of HVDC system. So we are going to see the major components only. The first comes the 6 or 12 pulse converter. Any HVDC system, the basic requirement is the converter system. Converter here refers to a rectifier or an inverter. Because we already have discussed the HVDC system, the main advantage of HVDC converter station is that The rectifier station will act as an inverter station. At the same time, the inverter station can also act as a rectifier station. So this is the possibility. That is why we are using the term called as converter, 6 or 12 pulse converter. So we will discuss in detail about the 6 pulse converter or 12 pulse converter in the next slides. And next is the converter transformer. The converter transformer is not as of the type of conventional transformer that we are using in the AC side, but it should have some design criteria which is different for this HVDC systems, because it has to work both on AC and as well as DC side. And third one is the filters. So we know why we are using filters. We need to mitigate the harmonics. So we need to have filters both on AC side and DC side to take care of the harmonic generations and also to reduce the harmonics. At the same time, these filters will support the reactive power compensation as well. So the filters on AC side and DC side, they will reduce the harmonics. For example, we may have first harmonic, third harmonics, fifth harmonics, and then 11th harmonics. Likewise, it will go on. All the harmonics can be reduced with the help of these filters. At the same time, it will support the reactive power requirement of the system as well. And then we are having something called as smoothing reactors. So smoothing reactors, we know always whenever there is a conversion from AC to DC or DC to AC, the ripples will be there. The ripples has to be mitigated. So for mitigating the ripples, DC ripples, we are using the smoothing reactors. So it is DC side to reduce the harmonic currents in DC line, and possible transient over currents are also the one of the advantage of smoothing reactors. And then we have shunt capacitors to complement the reactive power generated by the converters as they operate on lagging power factor and take the lagging current. The next one is obviously the DC transmission line or DC cables for the power transmission. So this is how a typical HVDC system will look like. So this is the AC bus from which the AC supply is coming, and here what we have discussed about the converter transformer. This is not same as the conventional transformer, but it is different for this HVDC system. And this is the converter station. This is one converter station, then this is another converter station, and this is the DC conductor, and we can see the AC filters and shunt capacitor for reactive power compensation. On the other side also, we have DC filters here, and we have smoothing reactor to reduce the ripples. On the other side, the same setup is there. We have converter station. This completely will become converter station, converter transformer, AC filters, and then what is that, shunt capacitor, all those things. And we are using some communication channel to communicate what is the current voltage and frequency that is being used there, the components of the HVDC system. So just to have a look how actually a converter station will look like. So this is nothing but thyristor valves refers to the converter station, how a converter station, typical converter station will look like. And this is the converter transformer, which is just for your purpose of knowing how it will work and how it will look like. I have just added up some photos. You can just Google it and find out many other photos are also available. This is how a typical converter station will look like. And then AC and DC filters with capacitor banks used for filtering out harmonics, reactive power compensation. Okay, and the HVDC smoothing reactors to smooth out the ripples of the DC converted values. Okay, so let us summarize the things that we have discussed in today's class. In today's class, we have discussed about the various types of HVDC links. We have discussed about monopolar link, we have discussed about bipolar link, and we have discussed about the homopolar link. And we have discussed bipolar link is comparatively advantageous than monopolar and homopolar links. And we have discussed what is the need for using this two conductors and why we are using two conductors. What is the problem with monopolar link? If there is any problem with any one of the converter, the monopolar link will completely collapse. But in case of a bipolar link, even if one conductor is having a fault, the other conductor can carry at least 50% of the power. And homopolar link also has the same advantage, but it is using completely negative polarity to again to reduce the effect of the coronal losses. That is what we have discussed in the categorization of HVDC links. And then we have discussed the basic components of HVDC systems. We have discussed about converter transformer, We have discussed about the thyristor valves and all the other things like smoothing reactors, AC and DC filters, and all the things. In the next video, we will be discussing in detail about the components of the HVDC system. Thank you, students.